Your lecturer is Dr. Stephen Ressler. Dr. Ressler is Professor Emeritus from the United States Military Academy at West Point, where he taught for 21 years. He holds MS and PhD degrees in civil engineering from Lehigh University. Dr. Ressler served in a variety of military engineering assignments in the United States, Europe, and Central Asia. He has focused his scholarly work and professional service in the area of engineering education and has won numerous national awards for engineering education and service.
When we think about modern engineering and technology, we tend instinctively to think about sophisticated computing devices and consumer electronics, about jet aircraft and bullet trains, about robots and lasers. But in many ways, the products of modern engineering that have the most substantial influence on our lives are the ones we almost never think about. The everyday technologies that surround us in our homes and workplaces, the infrastructure systems that have been so beautifully integrated into the fabric of modern civilization that they're practically invisible and are inevitably taken for granted. Consider a typical day in your life. Your alarm clock rings. You spring from your bed, excited to greet the new day. A glance out the window tells you that it snowed last night. You're glad it's Saturday, so you won't have to venture out into the cold for a few hours. You walk to the bathroom, flip on a light, and turn on the water to take a shower and brush your teeth. Then head for the kitchen to brew some coffee and grab some fruit from the refrigerator. A friend calls. He's on the road now, but he invites you over to his place to watch this afternoon's ball game. Hop into your car and drive across town to meet him. It's just a typical day in a typical week. And yet, in this simple series of everyday activities, you've made use of an amazing array of technological systems. Your home's structure supported 20 tons of accumulated snow on your roof. Your heating system and insulation kept your home at a comfortable temperature 50 degrees higher than that of the outside air. Your plumbing system supplied you with a stream of clean water on demand and then carried the wastewater away from your shower, sinks, and toilets into the municipal sewer system, which miraculously transformed this stream of foul effluent into water pure enough to return to a local stream without harming the fish. Meanwhile, a vast regional electric power grid supplied just the right amount of electricity, no more, no less, needed for your lighting, appliances, and hot water heater. This power originated in the chemical energy of coal that was extracted from an underground mine, shipped by railroad, and transformed into electrical energy at a sprawling power plant many miles away from your home. Your refrigerator provided precisely controlled cooling, which allowed you to keep a generous supply of perishable food on hand for immediate use. That call from your friend originated from his moving vehicle and was transmitted wirelessly from his mobile phone to a cellular base station, and then routed seamlessly through the public telephone network to your landline phone. In your drive across town, you took advantage of a wide array of automotive technologies, including the internal combustion engine, drivetrain, suspension, steering, and braking systems, all working in concert to keep your car moving and safely under control. Your car burned gasoline that originated in an underground reservoir of raw petroleum, which was tapped by a drill rig, pumped to the surface, piped to a refinery, and processed into fuel. You navigated across town with the help of the Global Positioning System, a small receiver in your car communicating with a constellation of satellites far overhead. But you have never reached your destination without an extensive system of roads, bridges, tunnels, and traffic control technologies, ranging from automated signal lights to railroad crossing gates. At your friend's house, You watched a television broadcast transmitted via a satellite orbiting 22,000 miles above the Earth's surface and captured by the 18-inch dish antenna mounted on his roof. And so, in just a few hours of a typical day, you used the products of at least 12 different engineering disciplines: civil, mechanical, electrical, environmental, transportation, chemical, materials, telecommunications, aerospace, industrial, mining, and petroleum engineering. And this is what everyday engineering is all about. The purpose of this course is to explore these everyday technologies that contribute to our quality of life in such a vital, if unobtrusive way. We'll conduct this exploration from an engineering perspective, with emphasis on how these products and systems work, and on the underlying science that influence their design and that ultimately determines how well they work. So, what is engineering anyway? Well, the answer to that question has varied somewhat through the ages. But as it's practiced today, engineering is the application of math, science, technology, and experience to create a system, component, or process that serves our society. Now let's spend a few minutes parsing this definition so we can go forward with a clear sense of what engineering is and what it's not. We'll begin by looking at the unique contributions of science, math, technology, and experience to the engineering enterprise. Science provides us with explanations about how the physical world works. Sometimes these explanations are true representations of nature, but often they aren't. For example, Newton's laws of motion serve as a scientific basis for the design of most of the everyday technologies we'll be talking about in this course, even though we know these laws aren't strictly correct representations of how physical bodies move in time and space. From an engineering perspective, Newton's laws are a lot simpler to apply than the general theory of relativity, and for most practical applications, their predictive power is entirely sufficient for their use in the design of engineered systems. Indeed, from an engineering perspective, the only things that really matter about a scientific theory are its predictive power and its ease of application. A historical case in point is the scientific theory of heat. Now, the first coherent theory describing heat as a form of energy equivalent to mechanical work was first published by Sir Benjamin Thompson in 1798. By the 1850s, the principal laws of thermodynamics had been formulated and were proving quite useful in the design of steam engines. Yet as late as the 1880s, scientists were still debating what heat actually is, with some claiming incorrectly that it's a fluid, which they called caloric, and others claiming correctly that heat is actually the motion of particles constituting matter. But even as the scientists debated, the engineers didn't care. They had a scientific theory that could predict the power output of various steam engine designs with reasonable accuracy, and that was all that mattered. To engineers, the predictive power of a scientific theory is so important because every engineering design is, at the most fundamental level, a prediction of the future. When an engineer designs a bridge, for example, he or she is predicting that the structural system will be capable of safely carrying the maximum load the bridge is likely to experience over its entire lifetime. And the basis for this determination is a series of scientific models used to predict internal forces, stresses, deformations, and material strengths. None of these predictions are perfectly accurate, but all are sufficiently accurate to produce safe designs. All of these scientific models are expressed mathematically because physical phenomena are inherently quantitative in nature. The great natural philosopher Galileo Galilei expressed this idea elegantly when he wrote, "Philosophy," by which he meant science. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language in which it is written. It is written in the language of mathematics. Mathematics is also the language of engineering because technological systems are envisioned, designed, specified, and constructed quantitatively. We need only look at this typical engineering drawing to see that this is true. So what about technology? Well, the relationship between engineering and technology is particularly fascinating because technology is both a means to an end and the end in itself. The product of engineering is technology, yet technology is also instrumental to the modern engineering design process. Virtually all modern engineering designs use information technology because the computational demands associated with our modern scientific models can be met far more efficiently by computers than by stubby pencils and electronic calculators. But stubby pencils and electronic calculators are technologies too, and they continue to perform an important role in modern engineering, as do all sorts of other technologies, like materials testing equipment, measuring instruments, and the machinery associated with manufacturing and construction. These tools of the engineering process are themselves all products of engineering. By the way, this same circular relationship also exists between science and technology. Science contributes immeasurably to the design of modern technology, and yet, modern science would be impossible without technological tools like electron microscopes, satellites, and particle accelerators. Now, its value notwithstanding, the role of science and engineering is sometimes overstated. After all, many of humankind's most important inventions and technological innovations have been created with little or no scientific basis. At best, the people who built the very first wheeled vehicles, water power, aqueducts, and cathedrals could only draw upon a qualitative understanding of the physical world. The invention of the steam engine preceded and actually inspired the science of thermodynamics. Conversely, the role of experience in engineering is often underappreciated. Consider the modern automobile, the invention of which is generally attributed to Carl Benz in 1886. The years since then, the sciences of mechanics, thermodynamics, chemistry, and electricity have contributed mightily to the development of this machine. But much of its long-term development must also be attributed to experience, careful observation, empirical testing, trial and error, and meticulous refinement, interspersed with occasional bursts of creative insight. This side of engineering has little to do with science and everything to do with ingenuity. The modern engineering enterprise is broad and highly diverse. Recall that my simple example at the start of this lecture touched upon 12 different engineering disciplines. Each of these disciplines has its own extensive body of knowledge and its own problem-solving approaches. As such, the scope of this course on everyday engineering could be impossibly broad. I've attempted to address this challenge with a simple organizing construct. In this course, we'll restrict our exploration of everyday engineering to the major technological systems you're likely to encounter in and around your home and during a short drive across town. We'll begin by focusing on the house itself. We'll look at the typical American single-family residence as an engineered system consisting of 8 distinct but interrelated subsystems: structure, foundation, building envelope, site, plumbing, electrical, heating and cooling, and telecommunications. Now, several of these subsystems are integrally connected to vast infrastructure networks. Your plumbing to a municipal water supply and sewage system, your electrical system to a regional power grid, your phone to the public telephone network, and we'll explore these large-scale engineered systems as well. Within the home, we'll examine a few representative examples of the thousands of simple machines and gadgets you encounter every day. We'll take a look at the principal technological systems used in your automobile, and then we'll hit the road for an overview of roads, bridges, tunnels, and transportation engineering. And then finally, we'll wrap up with a look at the technological challenge of solid waste disposal as a lead-in to an overview of the brave new world of sustainable engineering design, and some reflections on its implications for our everyday lives. Arthur C. Clarke, the renowned science fiction writer and futurist, once wrote, "Any sufficiently advanced technology is indistinguishable from magic." But I disagree. No doubt, technology can sometimes seem both mysterious and intimidating, but we can all understand it. We can distinguish it from magic if we just devote ourselves to the task. For each of the technologies we'll explore in these lectures, we'll attempt to answer three big questions. First and foremost, how does it work? Second, what are the key scientific principles on which its design and operation are based? Third, because no technology is perfect, how and why does it sometimes fail? Now, in defining the scope of this course, I'll add three important caveats. First, this is not a history course, so we generally won't explore the historical development of the technologies we address. I have found, however, that historical development can sometimes be a very powerful tool for enhancing understanding of a technology. And in such cases, I've happily included it. For example, the fourth generation cellular telephone of today is almost indistinguishable from magic. On the other hand, the simple first generation phone of 1983 or so is actually quite understandable. Thus, if we start with the 1G phone and then examine the three successive incremental improvements, 2G, 3G, and 4G, we'll ultimately be much better equipped to appreciate the current state of the art. Second caveat, some aspects of everyday engineering in the US are quite different from everyday engineering elsewhere. This is particularly true for residential construction and electrical power. Where these differences exist, I'll do my best to call attention to them, but for the sake of time, our focus must necessarily be on the US version of these technologies. And third, this course will not address computers or home electronics. Clearly, these technologies are both important and prevalent in our everyday lives. However, I'm unable to address them in this course, in part because they're just too far beyond my own expertise, but also because they're sufficiently distinct from the topics that I will be addressing that they truly require courses of their own. Fortunately, the Great Courses does offer a superb lecture series called Understanding Modern Electronics by Professor Rich Wolfson. If you're interested in the subject, I do hope you'll check it out. So why is everyday engineering a subject worth studying, even if you're not an engineer? Well, I'd like to offer three reasons. First, we can all benefit from being informed users of technology. When you're shopping for a new car and looking at a set of engine specifications like this one, it would be helpful to know what these terms, displacement, horsepower, torque, and compression ratio actually mean. To know the difference between a dual overhead camshaft and a single overhead camshaft, and the difference between direct and multi-port fuel injection. When your building contractor tells you that he's going to insulate your walls at R19, well, you really ought to know what an R value is, and whether the potential energy savings might justify paying for more than R19. When your plumbing system breaks, you'll benefit from understanding what went wrong, even if your plumber will be doing the repair. If nothing else, you really ought to know that just inside one of your walls, there's a valve, like this one, which can be used to shut off the water supply to your entire house. Knowing where this valve is located is a reasonably good alternative to the thousands of dollars in water damage that could happen between the time when you first noticed the leak and the time when the plumber actually arrives. Second, knowing something about everyday engineering can make us better citizens. On the day I started working on this lecture, this issue of my local newspaper arrived at my doorstep. And quite appropriately, all three of the main front page stories were directly related to topics covered in this course. On this day in Pennsylvania, the state's Public Utility Commission implemented a new regulation that drastically improved individual consumers' ability to switch from one electric power supplier to another. The regional utility companies vigorously opposed this plan. On this day, the State Department of Transportation announced the approval of a $250 million project to widen a major highway that suffers from serious overcrowding. But because the project is being funded with gas taxes and higher tolls, it was opposed by many local politicians. And on this day, several municipalities initiated a case with the state superior court challenging the constitutionality of the state's oil and gas law on the grounds that many incidents involving shale gas wells polluting local water supplies weren't being publicly reported by the state's environmental regulators. These are challenging issues with complex economic, social, political, and environmental implications. And as an engaged citizen, I should take well-reasoned positions on issues like deregulation of the power industry, public investment in transportation infrastructure, and environmental impact of shale gas exploration. And I should consider these issues when I vote for the officials who influence these policies. But can I really take a well-reasoned position on any of these issues without some understanding of the associated technologies? For example, can I reasonably oppose fracking if I don't even know what fracking is? Third, and perhaps most important, everyday engineering is worth studying because it's just immensely rewarding and just plain fun to learn about the world around us. There's nothing new in this, of course. Many people, myself included, find great satisfaction in identifying stars in the night sky, in distinguishing a red-tailed hawk from a turkey vulture, an oak tree from a red maple, a piece of granite from a lump of quartz. But I've always been just a little disappointed that most people don't seem to have the same enthusiasm for the technological world as they have for the natural world. The technological world is certainly no less interesting. Perhaps the problem is just that we technology enthusiasts don't have the same sorts of information resources that are so readily available to stargazers and birdwatchers. I hope this course will provide just such a resource by serving as a sort of field guide to everyday technology. Today, if you notice this utility pole at all, you probably see little more than a tangle of wires. But by the end of this course, you'll be able to discern 3 high voltage power distribution feeders, 3 insulators, a neutral wire, a transformer, a fuse, a low voltage distribution line, a telephone cable, a fiber optic line, and a structural guy wire. You'll also be able to distinguish a highway cloverleaf from a flyover interchange. You'll recognize this structure as a water supply tower and this one as a sewage clarification tank. And I hope you'll take great satisfaction in doing so, simply because these various species of everyday technology are integral components of the built environment in which we live, work, and play. Now, as we explore the world of everyday technology over the next 35 lectures, we're going to encounter some recurring themes. I'd like to conclude today's lecture by raising your awareness of these 4 threads of continuity, so perhaps they'll be more meaningful when we encounter them again later in the course. First theme, there is no such thing as an ideal technology. Engineering always involves trade-offs. To achieve an optimum solution with respect to one criterion, we must inevitably compromise on one or more other criteria. For example, as a fuel for generating electrical power, coal is cheap, plentiful, and particularly well suited for generating large, steady power output 24 hours a day. But coal is also the most environmentally detrimental energy source in our current portfolio. On the other hand, renewable energy sources like wind and solar are far more environmentally friendly, but they have the significant disadvantage of only producing power sporadically when the wind is blowing and the sun is shining. And because we currently have no technological capability for large-scale power storage, renewables aren't currently capable of meeting our total energy demands. We'll encounter these sorts of engineering trade-offs in every single lecture of this course. Second theme, our collective love-hate relationship with technology. We love the conveniences afforded by abundant electrical power, but refuse to buy a home anywhere near a high-voltage transmission line. We support increased generation of renewable energy, as long as those offshore wind turbines are built along somebody else's favorite stretch of coastline. We're addicted to our cell phones, but we'll vigorously protest the construction of a new cell tower in our neighborhood. In this course, I hope we can reconcile these sorts of contradictory positions, just a bit. I know I can't convince you to like that ugly cell tower, but I can explain why it needs to be right there, why it must be tall, and why it doesn't necessarily have to be quite so ugly. Third theme, the substantial role of government in everyday engineering. Throughout this course, we'll see the impacts of government regulation in implementing the building codes that govern the design and construction of our homes, the engineering standards for highway design, water quality, and energy efficiency, and even the operation of that traffic light at the end of your street. We'll also see how deregulation has reshaped the US electric power, telephone, and railroad industries, and has significantly influenced the services we receive from these industries. We'll see how government incentive programs have been used to spur technological development, sometimes for better, sometimes for worse. So, is government involvement in everyday engineering a good thing or a bad thing? Well, if you answer this question from an ideological perspective, there's a clear yes or no, depending on your political orientation. But if you answer it from an engineering perspective, the answer must be far more nuanced. As we'll see, the impact of government involvement depends on the specific government action, on the context, on the interface with relevant professional communities, especially on the technology itself. Final theme, and by far the most important. In developing this course, I've been struck again and again with a sense of wonder at the remarkable human achievements reflected in these seemingly mundane works of everyday engineering. Our beautifully integrated systems for residential construction, water purification, electrical power distribution, telecommunications, and transportation are triumphs of human imagination, ingenuity, and persistence that substantially improve the quality of life for millions of people. They may not be indistinguishable from magic, as Arthur Clarke suggested, but they are magical. As you experience these human achievements in the lectures ahead, I hope you'll gain a keener appreciation for the works of the countless engineers who've done so much good work, largely behind the scenes, to make our lives better. They are in many ways the unsung heroes of our technology-intensive world. Indeed, I can think of no better way to reinforce this point and to conclude this lecture than to recite an excerpt from Rudyard Kipling's wonderful poem, The Sons of Martha. This title is an allusion to the New Testament story of Mary and Martha, two sisters who were visited by Jesus and responded in very different ways. During the visit, Mary sat at the Lord's feet, listening to his words and enjoying his company, while Martha was preoccupied with the household chores. The poem is Kipling's tribute to the engineers of his day, whom he characterizes as the sons of Martha. Here's the excerpt. They do not preach that their God will rouse them a little before the nuts work loose. They do not teach that his pity allows them to drop their job when they damn well choose. As in the thronged and lighted ways, so in the dark and desert they stand, wary and watchful all their days, that their brethren's days may be long in the land. Raise ye the stone or cleave the wood to make a path more fair or flat. Lo, it's black already, with blood some son of Martha spilled for that. Not as a ladder from earth to heaven, not as a witness to any creed, but simple service simply given to his own kind in their common need. As it was in Kipling's day, so is the work of the engineer today. Simple service simply given, yet also heroic in a quiet, unobtrusive way. Next lecture, we'll learn how the simple service of the engineer is manifested in the design of your house.